the exam had 5 questions, I believe, which are really elementary questions. The only problem that may have some work maybe are number 5, right?
Yeah.
Because that,
So many
you know, you
times.
give 4 easy ones and then you throw in a number 5, which is kind of, you know, it's many steps.
Yeah, I have to reprint out my page because I erased it sometimes.
So, you know, the first one you had 2 parallel plates separated by a certain distance. One plate is maintained at 1,000, the other one at 500. What is the radiant exchange? That takes 2 seconds to do. You know, it's like here, 2 plates, half a meter apart, 1,000 meters, 500 meters. What is the thing? The only thing you have to make sure is you get a friction, not a friction factor, a shape factor or a view factor, okay? Because not all the radiation that's coming out of one is going to be intercepted by 2. By the way, the view factor or shape factor F is just like emissivity. It has to always go from, what's the minimum value? It should be 0, right? You can either see nothing or see the entire thing. When you have 2 surfaces exchanging energy, right? They can either exchange all the energy, in other words, all the energy leaving this surface gets absorbed by that surface, gets received by that surface, or none of it, okay? So F is always between 0 and 1, okay? So in this particular case, because there is a certain spacing, obviously not all of it, unless the spacing is like 1 millimeter or something like that, then you can probably say the shape factor is pretty close to 1, right? But as the 2 surfaces get separated, what happens to the radiant exchange? It goes down because less and less. So the way you find that F12 is obviously to use those figures in the chapter 13 between 2 parallel plates. Obviously you need to find what L is, what X is, find X over L, find Y over L, and then just read the value of point F12. You may read 0.28, you may read 0.29, but as long as it's kind of in that neighborhood, that's good enough. And then it's just a matter of plugging in the values. Sigma A1, F12, T1, T2 over 4, and then making sure that the temperatures are converted to Kelvin instead of kept in degree C. Okay? So that's all in problem number 1. Problem number 2. Problem number 2. I can't even see. Oops, that's not what I want to do. Yeah. 2 infinite parallel plates. Infinite parallel plates are maintained at 200, 300. What is the net head exchange? Obviously, when they are infinite, you know that everything that leaves one gets received by the other. And then you're asked to repeat if both temperatures are lowered by 100 degrees. So, what is the solution for that? Well, come in here. Now there is the F12 is simply just 1, so that's no big deal. So Q12 over A is sigma T1 to the power 4 minus T2 to the power 4. So when they are separated like that, as infinite plates, with these temperatures, obviously the heat flux or the heat exchange is 30 to 77. Now, if you reduce each one of these temperatures by 100, so instead of 573, it should go to 473. Instead of 473, it should go to 373. But the equation is exactly the same. So all I did here is reduce the temperature by 100, and you can tell that if the temperatures are lower, the radiant exchange between the surfaces has to be lower, and in fact, it became 1742. Now, if you take the ratios of the 2, you find it's 53. So the second one is 53% of the first one. That means that you had the reduction of, obviously, 47 from 1 to 2. All right. Now, problem number 3 was kind of maybe a little confusing. I don't know. problem number 3 said you have a cylindrical cavity. It's a cavity, okay? So it's a hole. Okay? So this is kind of the outside, right? So there is nothing in here, you know, it's a cavity. That has a diameter D and it has a length L, and it is machined in a machine block, okay? The conditions are such that the base temperature, the base and the side surface is at 1,700, okay? So we have here 1,000 and 700. Approximating the surfaces as black determine the emissive power of the cavity. So the emissive power of the cavity, I mean, we're usually talking about a surface that is just one surface that emits, right? But in here, what's really happening? This one is emitting and that one is emitting, right? But I'm only interested is what's coming out of where? Out of the top, what exits the top, okay? So, again, with that thought in mind, see, this is my schematic in here. This is my cavity. This is the base, which is at a temperature of 1,000. This is the side, which is at a temperature of 700, with all the appropriate dimensions. And I'm trying to figure out how much is coming. So at the bottom surface, I call it A1. The circumferential area, I call it A2. And then the top area, I call it A3. Okay, so what am I looking for? I'm trying to find what is the emissive power of the cavity. And you know, because all the surfaces are blacks, you know that the emissive power is simply E is equal to Q, that's coming out of 3, right? Divided by the area out of 3, okay? So, and then you go like Q3 is simply A1 F13, because whatever is coming out of 3 is, first of all, what is coming out of A1 that gets exchanged with area number 3, and we know what that is. A1 EB1, when I say A1 EB1, that means that A1 sigma T1 to the power 4, right? But what gets exchanged between 1 and 3, I have to always multiply it by F13, okay? That gives me the amount of E that's going from A1 that's coming out of here and going through here. Then I need to look at the one that's coming out of there that's going through area A3. That's going to be A2 sigma T2 to the power of 4, right? And I have to say it's the fraction. Remember the way we read this, Fij. The fraction of the energy leaving 1 that arrives to 3. The fraction of energy leaving 2 that arrives at 3. That's what shape factors are, okay? So that's why the amount of energy that is coming out of the top of the cavity, which is A3, is simply the fraction that's coming from the base plus the fraction that's coming from the side, okay? Now, you look at this and you go like, F23 and F13, because there is a symmetry, F23 is equal to F21, and again, using reciprocity, remember AI Fij is equal to AJ Fji. In other words, F21 is equal to A1 over A2 times F12, and then using the fact that F12 is equal to 1 minus F23, now you just plug in all the values in there, because it's just a matter of finding what the F's are, right? Now, you come in here, we have the equation, which is a function of T2, T1, T2. Everything is known. The only one that is not known is really F1 to 3, right? And the way you do this is you, again, use the charts, right? Some of you use the equations, which is fine. So figure 13.5 is the one that shows 2 disks, you know, one on top of the other. Again, you have to find what L over Ri is, what Rj over L is, because that tells you where you should be in the thing. And then you find that F13 is approximately about 0.05. Now you're ready to finish your calculation, okay? So it's it's not the type of problem that has just one equation and you immediately do that. Anytime you do radiation calculations that have shape factors, you have to see how much leaves one surface that gets to another surface. Number 4, kind of in that same idea, for number 4, what it says, you have a large enclosure, it's a black enclosure, consists of a box. Surface 1, which is at the bottom, is at 262. Surface at the top is 177. And all vertical surfaces, including the back wall. The back wall is surface number 3. Okay? It's not the entire stuff. So what you need to figure out is really what is Q12 and what is Q3. And those are the main questions that are associated with radiation calculations, is to find the radiation exchange between two surfaces. So, schematic again plays a big role. It's a cube, right? This is the bottom, which I call surface number 1, right? Surface number 2 is the top surface. These are the key dimensions, right? And then the back surface is surface number 3, right? And is at a temperature of 478 or 205. So what is Q12? Since you know the temperatures, it's essentially a problem that involves finding what the view factors are. In other words, what the F value is. So, if I want to do between 1 and 2, these are what you have: 2 square surfaces or 2 rectangular surfaces spaced by a certain distance. So your job is to look at that figure and to identify what is X, what is Y, what is L, find X over L, find Y over L, and then be able to read the value of F12, period. You know, that's all there is to it. So once you find F12, then finding what the heat transfer is going to be is really not a problem. And then the same thing for Q13. Now you have two surfaces that are perpendicular and they share one edge. So it's the figure that is applicable for here is not 13.4, but it should be 13.6, I believe. Yes, 13.6, which is the main one that gets used in the last problem. Again, finding what X is, what Y is, what Z is, finding all those values, and finding what is the approximate value of F13. And then once you find F, then really the Q is really not an issue. Now, last but not least is, this one does not have any temperatures or anything like that. It's just a shape factor, okay? It's these two, there are no tables, by the way, that have this, okay? So the big question, why did I put this problem, is how can you make use of the other tables, the other shapes, to find what that shape is going to be, okay? So really what you have is you have 4 surfaces, you have all the dimensions that are given, and you're asked to find really how much energy, what is the fraction, because what F12 means is what is the fraction of the energy leaving surface 1 that gets received by 2. Obviously, it's not going to be 0, it's not going to be 1, right? But it's going to be something, right? And what is the big question here is you go, okay, how am I going to do this? Well, figure 13.6, because most of these surfaces are perpendicular to each other, right? So what you can do is you can combine these two surfaces, 2 and 4, and 1 and 3, and figure out what is the shape factor of this entire surface, right? Like, what is the fraction leaving 1 plus 3 that gets received by 2 plus 4? Okay, does that make sense? So you're looking at this, everything that is going from the bottom to the vertical surface. Again, by looking at figure 13.6, you find that it's 15% of the energy that leaves 1 plus 3 that gets received by 4 and 2. Now, we still need 1 and 2, so how do we do this? Well, then what we do is we can compute 1 and 3, but just to 4, not to, And this is not the only way, by the way, to solve this problem. There are many different combinations, okay? This just happens to be the one that I wrote there. So if you do 1, 3, and 4, again, using that same table, you find that it's 0.1. The amount of energy that leaves 1 and 3 that gets to 4 is actually equal to 0.1. Now, that means that the amount that leaves 1, 3 and gets to 2 is how much? It's just the difference, right? Between 0.15 and 0.1, which is 0.05. Okay, now we're getting close because what we figured out is how much is going from 1, 3 to 2. But I just want how much is going from 1 to 2, not from 1 plus 3 to 2. So that leaves, again, another possibility is to look at 3, this surface here, just 3, to 2 and 4. Okay, again, that same table, 13.6. 3 to 2.4, and then 3 to 4. 3 to 4 meaning just this guy. This to this, okay? Once you do that, then you use that subdivision method. That means F3 to 2 and 4 is F3 to 2 plus F3 to 4. Using that equation, you can find what F3 to 2 is, which is the difference between the two, which happens to be 0.075. Now, at the end, to find what F13 to 2, using the reciprocity rule, should give me immediately from this equation what F12 is going to be, which happens to be roughly about 0.425. So it's a little bit different steps, and usually when you have three surfaces here and 3 surfaces there, it can get pretty done quickly, very, very long, okay? So this one happens, you just have 2 and 2, and they involve the reciprocity rule, they have the subdivision rule, and all that kind of stuff. So, but if anything, you have to remember that the F, because that's really what chapter 13 was all about, is really about view factors. The view factors is an important thing that just measures the fraction of energy leaving one surface that actually gets to another surface. Okay, now, the project. The project, I'm not going to solve what the project is going to be, but I can give you the big guidelines, obviously. What the project involves is really the design of a heat exchanger, which I bet most of you will choose the counterflow versus the parallel flow, right? So what are you going to have? You're going to have the 2 fluids, right? And this, I believe, will be water, right? And this will be the benzene, right?
Yeah.
Because you're heating the benzene. I don't know what these temperatures are. So now I know the water temperature is 60 degrees,
And
right?
then it's 38 and 24.
38 degrees and 24 degrees, right?
Yeah.
And then the mass flow rate of this guy is given. I think it's 4,500, right?
Yeah.
Kilograms per hour, which happens to be 1.25
25.
kilograms per second.
Yeah.
So, the idea, the big idea, is really to design something. That means you need to specify what? Cross section and the length. I mean, that's the basic quantities really are cross, you know. Good. Now, the first thing you need to figure out in here is that you can calculate immediately is what?
The
With the
exit
information that is given.
exit temperature of the water.
Uh,
Oh, that's given right now?
Yeah.
The Q.
The Q, exactly. That's the first order of business, is really to find what Q is, right? Because Q is going to be equal to m dot C times CPC times T hot out, right?
Yeah.
No, T cold out,
Cold.
sorry. T cold out minus T cold in, right? This is known, this is known, this is known. How about this one?
Yes.
It is known. From the data that I gave you, you should be able to interpolate that value, okay? So you should be able to get a pretty hard value there for Q, right? Now, okay, then what should be your next step? There are two different ways you could go, right? We have, remember, in your mind, what should work in your mind is that you have an equation that says Q is equal to UA delta TLM, right?
Yeah.
Now, delta TLM is what? It's the
Log mean temperature.
log mean temperature difference. And log mean temperature difference requires how many temperatures?
4.
4. And how many do we have?
3.
We have 3, okay? So how do we find the fourth one? Maybe energy balance?
Yeah.
Okay, so, so energy balance, which says that this Q, right?
Basically, the Q of the hot equals Q
Yeah.
cold, right?
Q hot is equal to Q cold, right? Which is m dot times hot, which we don't know,
Right.
times Cp of the hot water, of the water, right? Times T hot out minus T hot in. Now, obviously, the only thing you know is the inlet temperature of the water, and the inlet temperature of the water is going to go up, and the temperature is going to go down, right? Now, how are you going to calculate T hot out? Is it calculated like that, or you have to iterate, or
Like
what
to
do you-
iterate, or like interpolate.
interpolate and play around until you make sure that that thing is fine. Now, do you choose how about the mass flow rate of the hot water? How do you
You'll
figure that out?
Find that based on your, based on the temperature you choose. You can solve for your mass flow rate and then make sure it falls within your velocity.
Remember that velocity thing,
Yeah.
right? So for example, here, with this, the hot one, I mean the benzene one, shouldn't be really a big deal because, I don't know, if you have the mass flow rate, right, for the benzene, for example, I don't know where you want to have the benzene flow, whether it's inside or outside. It doesn't really matter as long as you choose what you need to choose. But you know that the mass flow rate so for example, you know that the velocity or m dot is equal to rho, right? Times the cross-sectional area times the average velocity. This equation always holds for flow in pipes. Whether you're talking about the annulus or whether you're talking about the central part, right? Now, do we know the mass flow rate of the benzene?
Yes.
Do we know the density of the benzene?
Yeah, you can interpolate.
Interpolate,
Yeah.
because you were given
Yeah.
specific gravity in the table, right? And how about the velocity?
Range.
There is a range, right?
Yeah.
So maybe you start with, you either do it in Excel or you choose as a starting point, some middle value or something like that, right? So you don't want to be at the edge. So once you select the V, then you can figure, at least get the first idea of what is the cross-sectional area for the benzene, right?
Mhm.
Now, once you find that cross-sectional area, you know, what some people do sometimes to make the equations even better, maybe you find 1.33 or one, I don't know what value you're going to find. Some people look at regular sizes of pipe in pipe, you know, and then choose an existing one that has that particular inside diameter, right? Inside, you know, area, right? Because with this, you can actually figure out what the radius or what the diameter is if you have, let's say, the benzene flowing in the inner pipe, right? And then from there, you may choose at least a pipe within a pipe, one that has an area that is pretty close to that, because at least you know it's available, you can just get it out and use it, okay? So, A and then A adjusted, right? Once you get A adjusted, obviously the, now you're fine. That means you really have adjusted the velocity, right? That's why I said don't start with the edges, you know. Once you find this, then you can figure out another way is to come back here and try to find what is the outward temperature. I mean the outlet temperature of the cold water. You may have to iterate on that one,
Yeah.
right? And then you may have to choose, because now, I don't know if you have the benzene flowing inside or if it's flowing outside, it really doesn't matter, because if you choose an average velocity for the water, right? And then with the chosen mass flow rate of the water, right? You can figure out what the area of the water is going to be,
Yeah.
right? And then once all these kind of square away, then you can use this mass flow rate in this equation, right? To maybe find what the temperature of the hot water out. Once you find the temperature of the hot water out, what can you find afterwards?
The L.
Well, not yet. You can find the delta T Ln.
Yeah. So that's what
Yeah, the log mean temperature difference.
Yeah.
Now, we're still not finding our length yet, right?
Mhm.
Because hopefully by the time you reach here, you have a cross section that's gonna probably look like this, right? Right? In which one fluid is flowing here, right? And then another fluid is flowing there. So what's the next step now?
Find your area or your total. Oh, from your area you can get your length.
But but these areas are what? They are cross-sectional areas.
Right.
You cannot find a length from a cross-sectional area.
It doesn't matter what different.
So how are you going to find the length of the pipe? Well, that's where this equation comes into the game. Remember? In that equation, what you have is Q is equal to UA delta T Ln, right? Now this UA is a function of what? Remember, you have remember in 1 over UA
Is there
is equal to 1 over HIA, right? Plus, what was it again? I don't know if you are considering maybe the thickness of the pipe. I don't know. Some of you may neglect that. T2 over D1 over 2 pi KL, right? Plus, what is it again? 1 over H out, K out. fact, from your book, it should be equation, let's see. Chapter 11, right? Chapter 11 on page, for equation.
11.5.
Very good, 11.5, yeah, log of 1 over HIAI. So equation 11, did I write it correctly?
There's two missing. You have two extra.
2 pi KL, right? What is my?
Well, they have the RFI over AI and RFO over AI.
Yeah, those are the fouling, I'm not considering those,
Okay.
you know. You know, you feel free to consider them if you wish, but that's equation, I'm just gonna write equation 11.5. Right? Because this area here, that's where the length is going to come into the game,
Yeah.
okay? The area here, if I kind of extend this guy here, if this diameter, I call it, let's say, DI or whatever, right? So the area is the circumferential area. So what is the area here equal to? It's going to be equal to the perimeter pi DI times the length, okay? Now, do you know that DI? Yes, because you have selected already previously, you know, what is flowing where, right? So you know the stuff. So to find what 1 over UA is, or UA, then since the area here is a function of L, there is an L, right? There is an L here. So your problem is really to find what HI is and what H out is. That's the part that you're missing, right? So how do you find HI and H out? How do we find these?
You can do well, it depends on if it's.
The regular stuff, remember?
Yeah.
With the Reynolds, find the Reynolds number,
Yeah.
calculate the Reynolds number, right? Remember the way we calculate convection? Find the Reynolds number, figure if the flow is laminar or turbulent, select a Nusselt number. Once you calculate the Nusselt number, then you can get H. You do that for both the interior pipe and for the annulus. That's why I said look at chapter 8. Once you find that, then using this equation will have only one unknown in it, which is the length. And you're done. In a nutshell. So,
Okay.
I hope it's at least a little bit more direction.
Yeah, that's a lot more direction.
I did mine a little bit differently, but
If you didn't calculate, you didn't calculate HI and H?
No, I did.
Oh, okay.
But what about solving my, checking my velocities, getting my, cross-sectional areas?
Okay.
I think,
But again, I'm not saying this is kind of the thing, you know, but at least it has all the elements that should be.
Yeah, it has all those components.
The components, yes.
Calculate a little different.
Okay. So I'm gonna keep it like this, you know, this, just kind of more direction and then we move on after that. Okay, now, the next, so we talked about this, talked about that, talked about the project somehow, let's talk about these two labs now, okay? Lab number 9 is going to be a quick lab that should be we know that Q, so lab number 9, lab number 9 says that I is equal to 1 over B squared. In other words, that Q is proportional to 1 over B squared. In other words, if I have my famous, again, 2.5 inch by 2.5 inch surface, right? That I'm going to bring into a certain temperature, right? And I'm going to have my thermopile in here. So as this reaches a certain temperature, it's going to start radiating. Of course, it always radiates, right? But then, as the amount of radiation that we read here is going to be in millivolts, as you know, right? The millivolt that we read essentially tells us what is the amount of heat, what is the amount of heat that is coming out of that, out of the, oops. So our table is going to be fairly simple. This surface, by the way, by default, this distance is 10 inches when it's kind of pushed way to the front, right? The main distance between this, where you're sensing the temperature, the heat, and the surface is 10 inches, okay? So our tables is gonna look like this. We're gonna have D, 10 inches, right? And then here, what we're gonna be reading is actual reading, okay? So when we fire that up, you know, maybe we're gonna get a certain value in here, right? And then, if you look at the table in your stuff, it says here, predicted, right? And then here, it's percent error. So for the first reading, obviously, we're not gonna predict anything because it's whatever it is, right? Now, the big question is, what happens if, let's say, for example, I get here 7.5, let's say. This is not gonna be the correct number, by the way. This is just so we know. What do you think the number here at 11 is going to be if this equation holds? So how are you gonna figure out what is the predicted value? For 11 or for 12? It's proportional to 1 over d squared, right? That means as the distance increases, what happens to the millivolts? Is it gonna increase or decrease? It's gonna be decreasing, right? So this is going to be 7.5, times 10 over 11 squared. You know, so remember, if you have Q1 equals that proportional to 1 over D1 squared, right? So Q2 is proportional to 1 over D2 squared, right? Let me call this Q1, right? So if I take the ratio of these two, what do I get? I get Q1 over Q2, or maybe Q2 over Q1 is equal to what? It's D1 squared over D2 squared, right? What does this mean? This means that Q2 is always going to be equal to Q1 times D1 squared divided by D2 squared. So here it's going to be whatever that value we read is Q1, right? Times 10. How about here? It's going to be Q1 times 10 over 12 squared, right? And then 13, you know, and so forth, right? Q1 over 10 over 13 squared. So this is what we're going to be doing in the lab. Once we reach this value here, whatever this value is going to be, which is Q1, then before we push that thing back, we will calculate this. Hopefully somebody has got a calculator. And then we'll just read it. And then obviously doing the percent error, you know how to do the percent error, right? So that's, that lab is really straightforward, and I think we do that until, and we don't have to wait, by the way, because it's already in equilibrium, so you just move it, like 3 seconds later, you just read the value. And, okay? Last but not least is lab number lab number 10. Lab number 10 is going to look at a fin transient heat. So we're going to have 1, 2, 3, 4, 5, 6, 7, right? So we're going to have a fin which is, I think, 2 centimeters in cross section, and then the distance between these thermocouples is 5 centimeters. So this is 1, 2, 3, 4, 5, 6, 7. So what we're going to have, I don't know if 7 goes all the way to the end or 4, we don't care. So we're going to have that, and then the way we're going to study this, because it is transient, as it stands now, let's say the room temperature there is 27 degrees, well, then all the nodes will be at 27 degrees, right? So what we want to see in here is this, this is, by the way, in stainless steel, right? Stainless steel. So what we're going to do is we want to try to bring this temperature here at node number 1, or subject the base of the fin to a high temperature. How the heck are we going to do that? And maintain that temperature, and then see how the temperature is actually going to be moving across this. So the way we're going to have this is I have a thing that's got a little cup in here, right? So the way we're going to do this is, as it stands now, it's empty, right? So at time t equal to 0, what we're going to do is pour boiling water in here. But in order to keep that boiling water at the temperature that is decent, near 100 degrees, right? So what I'm going to have is I'm going to have a temperature controller here. A temperature controller, you know, it's like PID controller, you know, that I'm going to put there. And then as soon as the temperature goes like 98 degrees, I have a submersible heater, right? That gets activated, you know, to add heat to the water, right? And then when the temperature reaches 98.5 or 99, it stops. So, you know, it's not going to be very exact, but at least I'll show you how that goes. And then the only data that we're going to be taking in there is that when t is equal to 0, right? Every 3 minutes, we're going to read temperature, thermocouple 1, thermocouple 2, thermocouple 3, all the way to thermocouple 7, okay? So we're just going to read those values for the temperatures, right? And then the idea, because it is a function of time, right? Obviously this node here is not going to feel much until maybe some time later. You know, most of the stuff occurs here. But then the only data of analysis that you have to do here, not much at all, is really just to plot the temperature profiles, you know, as a function of time, you know. So you just get the data and just put it in Excel, and that should do it.
I like lab reports like that.
Okay. So these 2 labs are not going to be much involved. So with that said, because we are already 4:10, let's start. Unless you have any questions or.
How many minutes are we gonna do on that one? Because we've got up to
What?
39 minutes. but-
No, we're just going to use this data for the second one. You know? But we're going to do maybe 2 readings.
Okay.
You know, just to kind of get a feel of what it is. But the data that we're going to be using is the one that I put in on Canvas.
Oh, okay.
Yeah, it's already there.
Yeah,
on
it's
Canvas.
there.
Right. In fact, it's right.
You
get one of those? It's already here.
Okay.
So we don't have to wait.
Cool.
You know, to get the same stuff. All right, so let's move on to. So we just need to activate this one first before we go on to that business there. So this one, you see, 10 inches, and then we're gonna move it to 11, 12, 13, etc. But before we do that, can anyone tell me what is it 70 for, I mean, for the variac or? what
It's
is it?
blank on the sheet.
Yeah, it's blank.
It's blank, alright. But in the main lab, does it say?
I don't-
Well, it really doesn't matter.
Doesn't really
You know,
say.
we're gonna set it at 70. So the variac is at 70.
Yeah, the previous ones you did 70.
Yeah, so we'll just keep it at 70, and I'm gonna turn this on. And just gonna push these guys back. So this number should be increasing, right? And this temperature here should be increasing. It is now at,
It says 70 right here.
what is it, 120?
That's with the
130.
temperature of the plate.
Temperature of the plate, yeah. So
120.
that temperature is gonna go up, I think, all the way to about 400, but we don't care, we'll just wait. So now just wait until this guy stabilizes, okay? So we've done this before, it shouldn't be an issue, right? So while this guy is approaching, because this is where we're gonna take our data, right? Let's take a look at this experiment. Now, this is the fin. This is that stainless steel rod, right? And it's got 1, 2, 3, 4, 5, 6, 7 thermocouples. Now, these thermocouples are, these thermocouples are attached. So I put this together last summer, you know. They're attached to same thing as those things back there. Remember, this is a thermometer,
Right.
digital display, and this is a thermocouple selector, okay? So as you go, you know, if you read thermocouple 1, which is right at the base, I go to 1, and then, you know, cycle through them, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now, as you can see here, this guy does not have anything on it, right? So this is my temperature controller, right? That's sitting there. As it stands now, it's probably just reading whatever this probe is doing. You know, if I hold it, I'm sure it's gonna go up, maybe.
Is that a good ambient temperature then? 26.7?
Yeah, well, pretty darn close, you know. In fact, it's probably these temperatures in here. I go temperature 1, 28.8, 28.8, 28.7, right? So already the temperatures that these guys are reading are pretty darn close, right?
So we should use it as an ambient temperature on
Yeah,
lab.
the probe.
But remember, for that lab is whenever we get to here, we'll read that.
Oh.
Right? So that's why I think I put in this down.
You call this,
Yeah. So when you get to this one, not that you need it anyways, but you know. Okay. Back in here. So my point that I was trying to make in here, that all these temperatures should be exactly the same, right? First of all, thermocouple 0 should read what? Nothing, out of channel, right? So again, I'm gonna cycle through each one. They are about 28.8. What is that value there? It's 4, 5, 6, 7. That one is kind of odd. And then 8 should be nothing, and 9 should be nothing. Okay, so now we're set up, right? Now, go back to number 1 here, which is still reading 28.8. Now, this temperature controller now is reading now whatever the probe is reading, and that's why we need to have the probe inside. Now, there is a setup in here. If you click on this, if I go to F1, the F1 function tells me at what temperature I should set this up. And instead of doing 100 degrees, which is probably not gonna happen, I did it at 98 boiling, right? So in other words, this guy is supposed to keep this temperature at about 98 degrees, okay? And if I do another setup in here, we'll only use the two functions, I think. Function number 2, oops, has kind of when it says 98, it has an error of 0.5. That means if you are at 98.5 or 97.5, you know, that's kind of the range, okay? So other than that, I think it's all great. So what are we going to do now? We need to get the base temperature to 100 degrees. With that, what I did is I put in this kettle, right? And now we need to turn this damn thing on. It should happen fairly quickly. Get the temperature, and then see the nature of the experiment is really not that complex, right? Now, as soon as this temperature here, I mean the temperature starts boiling, what we do is we pour it in here. This is the submersible heater that is connected to this temperature controller. So if the temperature goes below 98, it turns this on to add heat to the water to keep it at roughly the same temperature, right? So, and
So that's a heater.
it's a heater, that's what it is, right? Except that it does not emit, it does not provide heat constantly, right?
Right.
As soon as the temperature, we have a deficiency, right? So let me see what the temperature of this guy is. How much is that thing reading there?
6.6.
Okay, keep that in mind so just to see that it's not.
Mine's already 6.75 now.
turned off.
Hmm?
A little blue button on the pot.
This guy turned on. Yeah, but it's not boiling yet. So what happened to my temperature controller? Don't tell me. Back down on me.
Is it
Really this
the, I
part,
think it's
yeah.
this.
Yeah.
Oh,
Yeah, that light was off
what
now.
happened? Was it?
It,
That is weird. I didn't even touch it.
the sign.
All I did is like pull this guy here just to make sure that we need to connect this guy to here because I don't want to do it now, so it's not gonna heat up nothing, right? So here we are at 90, what is that? 86, almost.
Isn't it like these big ones? It's getting slower.
Alrighty, 95.8, 96.1. Now it's already boiling. 97, 98, 98.2, 98.5, 99.2. Okay. All right. So this one out in here. Now what I need to do is just pour this guy in here. Now because, obviously because of heat transfer, it's gonna start cooling down.
Mm-hmm.
Now I need to connect this guy, right? So what do you see in here? So my thermocouple is reading 90 degrees. Now do you see bubbles here forming on the stuff?
Yeah.
So what is happening? Because it sensed that the temperature is below the 80,
98.
on 98, and so therefore it is activating the thing, right? Now, so what's happening now to our temperature there for node number 1? It's going up. Obviously, it's going to be a function of time. So let's look. Why don't you cycle through all of them from 2? 2 should be lower.
Okay.
See, not much.
Mm-hmm.
Number 3. Look at number 3. See,
Yeah.
29.1. Not much sensing because the thermal conductivity is not that great for that. Keep going until you get to 7. See.
Pretty much what it was to begin with.
Yeah, 28.8 was pretty much our
Yeah.
thing. So those nodes at the end are probably not even feeling that something is happening here at the base,
Right.
right?
Can you feel it in,
Well, yeah, it's here if you touch.
oh yeah, that's hot.
That's probably how far
That's
it got,
Yeah.
right? And then the idea, because now this temperature front is moving, right? The idea now is to wait 3 minutes, so at time t0 we note all those temperatures, which are actually all 28.8, and then 3 minutes later we just go and cycle through each one of them, right? and then come back to node number 1, which should be going up, you know, all along, you know. So that's not, there is nothing really odd about this to speak of. And sometimes what I do, because you get some water that evaporates, you know,
Yeah,
I top it off a little bit, you know. But then this one is cooling off. Before topping it off, I want to make sure that it's, you don't want to put in some cold water. That reservoir is not that big, so you just increase the thing. And do you get kind of the gist of this experiment?
Yeah.
Okay, so there's no need then to top off or to do any stuff, okay? So, just add. Okay, is that thing,
Well, it just hit 9.6. It's been fluctuating.
okay, let's give it a minute or two, see if it
Yeah.
stops there. I'd like to have somebody with a calculator, that way I didn't bring mine today.
I, of course, I'm so one day I don't bring my calculator. Do we say we set the variac setting at 70?
Yeah, and in fact, it is in there. It's
Actually, they're
on
setting it
C.
up, as long as it's a
Set variac.
decent
Yeah.
number, that should be fine.
Yeah.
It's gonna fluctuate back down in a second.
It's 9 point. Okay, remember, as soon as you stop moving in front of it, it's
Mhm.
gonna start going crazy.
Right.
So,
So don't-
I think,
Well, when you went into the classroom, it was at 9.68, 9.67, then it went down to 9.65, and then it was going back up. I was like, oh yeah.
I think we're fine.
Good enough.
9.72.
Yeah.
So that's the, surface, did we already get the temperatures? I missed it.
Oh, what temperature?
The surface temperature and the ambient temperature?
Well, you can get the surface temperature if you need to, even though you're not gonna use it, but,
Oh, I mean, it's in the table,
yeah,
so you don't need it?
well, you might as well write it down.
Doing it right here. 26.7,
Okay,
what's surface? Oh, that's ambient,
ambient,
26.7.
7, and then the surface temperature. What the heck happened?
Didn't really move.
What was that?
Still
Climbing.
I was already doing calculations. Damn it.
I thought earlier it was increasing. Hmm,
Yeah, if we don't need it, then,
we don't need it.
okay, then it's
Okay.
not waste.
Okay, so, so what do we predict now
What did we
if
say?
we move, so it's the, what's the base reading now? Did we say 9.78?
I think it's whatever top you originally wrote down.
It was 9.72, but then our calculations are gonna be off from what it really is,
Oh,
our predictions.
Okay,
9.8.
9.8. Too afraid to walk over.
Okay, let's use that as our base number, 9.8.
9.8.
Okay, so what do you predict when we increase the distance to 11? So it should be 10 divided by 11, and then you square that number.
Is it 10 divided by 11 and square the whole number?
Square the whole number.
I
Yeah.
did it the backward. Okay. I did 10 divided by 11 squared.
Squared.
No.
Oh,
It's
mine
one
is
over-
wrong.
Yeah, because it's
But it's 1 over that?
there, but
So
when
is
you,
this whole,
no, this is correct. But when you compare one case to another, then you're gonna have D1 squared and D2 squared, just like it's written back on the board. How
So
much?
it's just 10 divided by 11 squared.
10 divided by 11, the whole thing squared.
8.099.
And then
so
you multiply it
8.1.
by 9.8. Right, 9.8.
8.099, yeah.
8.099, okay? So can somebody go move that thing to 11 inches? And then walk back in here.
It's 10 divided by 12 squared times 9.8.
Okay, why don't you walk back in here so we can get the same reading? So we moved it to 11 inches and we are reading what? 7.92?
7.92 we're reading it?
Yeah,
Yep.
pretty damn close. All right, so what is the value now for?
12 inches?
12 inches. So
6.81. And that's Q10
10 to Q10, yeah,
times 10 divided by 12.
the whole thing
The whole
squared.
so
Yes.
thing squared. Yes.
Okay.
6.81.
6.81, so let's
Okay.
check it out.
six five four?
654.
654. Okay.
All right.
So then the predicted is
5.80 for the next one.
5.80.
Yeah. I'm only going to 2 decimal points.
Yeah, that's totally.
Unacceptable.
You just got 5.80 blah blah.
Like
5.8, yeah, somebody needs to move it to 13.
I did,
Oh, you
Yeah.
did? Oh,
Yeah.
sorry.
yeah. So 5.43.
5.43.
Well, it's pretty consistent, the percent error so far.
Yeah, that's good.
And percent error, that's actual minus predicted divided by predicted.
Yeah, it's
Or-
difference divided by the
Oh.
actual, you know.
Okay.
And this one, the predicted for 14 inches is 5. 5.0.
Four 4.62.
4.62, okay.
Predicted for 15 is 4.36.
Like 3.90.
projected for 16 is 3.83. So I'm thinking 3.5 is 4. Ah!
Like 3.36.
Cool.
Okay.
Alright,
Was it kind of decent data?
Looks,
so I
yeah,
haven't
pretty
done
consistent.
impervious or percent error done.
Okay.
Probably see it. She says pretty
They
consistent.
look pretty close, they look pretty close.
Okay.
All right, that takes care of both labs.